AI just crossed the practical threshold. Diffusion is no longer stuck behind offline sampling. We're seeing it become a live control layer for music, video, and image translation, where latency, memory, and temporal consistency matter as much as quality. The big trend is clear. Researchers are decoupling, denoising, rethinking streaming architectures, and squeezing these models onto consumer GPUs without breaking fidelity. Stick around, because the details here show how close real-time generative systems are to becoming production tools. Let's explore the first paper, Daemon Diffusion Engine for Musical Orchestrated Noise. Daemon, from Daydream, turns ACE-Step 1.5, a diffusion music model, into a real-time performance instrument by adapting Stream Diffusion's ring buffer streaming design to audio and accelerating it with TensorRT. On an RTX 5090, it sustains 12.3 decoder completions per second for 60-second tracks, or 11.3 generations per second at the production depth of 4, while maintaining sample identical parity with batch decoding at the 16-bit PCM level. Its main novelty is a latency taxonomy for controllable diffusion. Per request parameters such as scalar denoise still obey an S-tick drain floor, but Daemon introduces per slot heterogeneous denoise scheduling, so a moving slider does not wipe in-flight generations. Shared mutable per step state for controls like SDE source blending, guidance, and X0, target morphing, which takes effect on the very next denoising tick, and a windowed VAE decode that cuts decode latency up to 8x by rendering only the playback window with overlap margins. Experiments show the per slot design preserves 100% completion under continuous slider sweeps versus 1.7% for a stream diffusion style Q reset, and the shared step controls produce true per frame gradients across 60-second outputs while preserving clap alignment and matching batch mode audio exactly. The paper positions the system as a controllable, low latency diffusion engine for live music, while noting that perceptual validation with musicians remains future work. Let's explore the second paper, Decoupled Residual Denoising Diffusion Models for Unified and Data-Efficient Image-to-Image Translation. Decoupled Residual Denoising Diffusion Models, or DRDD, from researchers at the University of Hong Kong, the Chinese Academy of Sciences, and the University of California, Santa Cruz, reframes image-to-image translation by separating Gaussian noise injection from semantic residual removal. The paper's key insight is that fixed Gaussian noise is not only a manifold lifting trick, but also a domain harmonizer that reduces feature divergence across tasks and domains. The authors formalize this with a KL divergence result, and then exploit it by splitting diffusion into a stochastic noise diffusion stage and a deterministic residual diffusion stage. In the reverse process, DRDD first removes task-specific residuals inside a noise-carrying domain, then denoises to the clean target, instead of entangling both operations in one coupled sampler, as in RDDM or I2SB. This design improves data efficiency because the denoising module can be trained only on abundant unpaired target domain images. Across all in 1.5 CDD 1.1 and a new multi-domain denoising benchmark called MNMD, DRDD is consistently state-of-the-art or competitive. On all in 1.5, it raises average SSIM to 0.916 and cuts LPIPs to 0.073, outperforming strong diffusion and non-diffusion baselines, such as DA-Clip, DiffuIR, VLUNet, and DFPIR. It also remains robust under severe data pruning, and the authors show the framework extends to DDPM, DDIM, and SDE-based diffusion backbones, such as IRSDE. The best performance appears when noise intensity is around 0.8 to 1.3, supporting the paper's central claim that controlled noise can be an asset, not just a nuisance. Let's explore the third paper, Sana Streaming Real-Time Streaming Video Editing with Hybrid Diffusion Transformer. Sana Streaming, from NVIDIA and MIT researchers, led by Song Han, tackles a hard limitation in video-to-video editing, maintaining source fidelity and temporal coherence while streaming minute-long, high-resolution outputs in real time on a consumer GPU. The core model is a 2B hybrid diffusion transformer that interleaves 15 gated DeltaNet linear attention blocks with 5 softmax attention blocks, combining constant memory global recurrence with local window plus sync refinement. This hybrid design cuts VRAM to 5.56 GB and makes the DIT core run at 58 frames per second. To train without paired long edited videos, the paper introduces cycle reverse regularization, where a forward edit is followed by a reverse prompt that reconstructs the original source chunk using a flow matching loss, improving long-range consistency and reducing drift. The system also distills a causal VAE decoder from the LTX2 VAE, so streaming decoding does not depend on future frames, and it pairs this with Triton-fused GDN kernels plus mixed precision quantization on NVIDIA Blackwell, yielding a 1.59 times DIT speedup over BF16 and 24 end-to-end FPS at 1,280 times 704 on a single RTX 5090. On OpenVE Bench, the method reports a 2.62 average score across the 5 spatial edit categories, outperforming prior systems such as OpenVE Edit and Lucy Edit while being far faster. The paper's novelty is the joint treatment of architecture, training, and GPU systems for real-time interactive video editing. That's a wrap on today's AI paper highlights. Thanks for watching.